Yeah, so then we're on to week number 4. So last week we saw the diffusion equation. That was the first one of our equations where we're introduced to the kind of idea behind the diffusion equation, and then the exercise was focused essentially on playing around with the diffusion equation to get a sense of how it works. And things are structured somewhat similarly this week, but instead of diffusion, we're going to be moving on to talking about advection and how that's mathematically formulated. And then the exercise this week, as you might imagine, will be then focused on, it's actually going to be a combination of the advection and diffusion equations, because advection by itself is not necessarily the most interesting. Although it's a somewhat challenging equation to solve, it's not really that interesting to apply by itself. So that's our focus, and we're going to see a couple different examples of how the advection equation applies to geological processes. And I'll show you that there's a section on the course page. I don't think I'll go through it with a lot of detail, but about how to solve the advection equation if you're interested to know how to do that. And then we'll have a look at this week's exercise. So I don't have anything planned in terms of like an interactive Python piece, but if there's questions along the way, if you want to like have me demonstrate something, or if you have a question about something Python oriented, then of course I'm happy to do that. I just don't have anything planned, because for this week's exercise at least, you don't need to have any new Python skills. So everything that we've done, or what we will do in this week's exercise, is stuff you have already seen and done before, with the exception of the equation that we're dealing with, of course. So we have 2 short sets of lecture slides. We can start here just with the kind of idea behind what advection is as a process, and a couple examples of how it can be applied to geological processes. So in this case, we're going to first see what the advection equation looks like, how it compares to diffusion, which we saw last week, and then see some application to a geological process. There are more possibilities of what I could include here in terms of examples of geological processes, but I think one is sufficient just to give you the idea of what the process is. So first off, just to talk about advection as a process and what it means. Well, in essence, it's just describing lateral, or even just generally movement of some quantity, which sounds very abstract in the way that that's described there. But that quantity could be, for instance, if you think about some kind of pollutant that's in a river floating downstream, it could be the movement of that plume of polluted water downstream. It could also be the movement of energy. So in this case, what's shown in the animation would be something more like advection of heat. So the kind of blue colors here are indicating, in this case, rocks that would be relatively cold temperature. Red would be relatively warm temperature. And you can see in this case, this is like a 2-dimensional model of 1/2 of the Earth's mantle, showing convection that's driven by heating at the base and cooling at the surface. And you see things like something similar to a plate sinking down at the surface and plumes rising up from deep toward the surface. As that fluid is flowing, it's carrying with it the heat and the energy inside of the rock that is being displaced by the flow of the fluid. And it's that process of moving the heat, in this case, that would be called advection in general. The reality is that what we're looking at in a model like this is not just advection, but it's a combination of advection and then diffusion, because typically when you move a fluid, let's say that's relatively warm, for instance, in the mantle from down near the core mantle boundary up toward the surface, the surrounding fluid or surrounding rock would be colder. So you start to cool once you've moved this warm rock up toward the surface, and the cooling takes place dominantly by diffusion or heat conduction. So when we talk about convection, and I'm sure the term, at least in terms of mantle convection, is somewhat familiar, convection is a combination of advection, which is the physical movement of the rock containing its heat, and then the diffusion process, which is essentially the rock cooling or heating based on interaction with the surrounding material. So it's in many cases when you talk about heat transfer problems with advection, you almost always have to also think about what's happening in terms of diffusion, because the heat that's being conducted away from the fluid once it's moved is a diffusion process. Depending on the time scale, you can sometimes ignore that, but generally speaking, as you can see in the animation here, I mean, when the material that's when the material that's cold near the surface sinks down, you can see the blue colors start to become more green and yellow as they're heating by the surrounding material down near the core mantle boundary. So you can see some nice examples, for instance, where these kind of plume-like things sink down from the surface, which would be like a subducting slab, and that material rapidly heats up in the surrounding mantle. Of course, rapidly being relative here, because this is probably over tens of millions of years, but you get the idea. So that's advection as a process. Last week, we saw the diffusion equation, which, as you might remember, basically comprised two parts. So the first was this idea that some flux Q is proportional to a gradient, for instance, in concentration. So this would be C, which we were using as our kind of generic letter to represent a concentration. dC dx would be the gradient in space in the concentration. And the proportionality that we saw last week was this capital letter D, which was representing the diffusivity or diffusion constant. And whether you consider that as a constant or whether you make it dependent on things like temperature can make things a little bit more complicated. But in essence, the simplest representation would be that we have some gradient multiplied by this scalar, which is the diffusivity. That was one part of our definition. The other idea was the sort of conservation of mass or conservation of energy, which was to say that any change in concentration, so this is dC dt, change in concentration with time, is equal to, in this case, minus dq dx. So this is the change in the flux in space. So if the flux isn't changing, in essence, that means that this term would be 0, which means that the concentration is also not changing with time. But if you change the flux of mass or of energy, then you're going to affect the concentration at some given location. And what you can see, for instance, here is that we have one equation that says Q equals this, and then we have a dq dx term, so we can substitute in the Q here, which then ends up being the second derivative of the concentration, because basically if you take dC dx, you take the derivative of it, you get the second derivative, which is then the curvature, if you want to think about it that way. I don't know how you guys think about these mathematical equations, but second derivative of concentration with respect to some spatial coordinate x multiplied by the diffusion constant. And here you have two negative signs, which is why this ends up being a positive for the change in concentration with time. But that's just substituting this Q in to the equation that we have here, which ends up with then the kind of classic form of the diffusion equation that is something we saw in last week's lecture. One of the kind of common applications for diffusion, as I've already mentioned, is to study things like heat transfer. So in this case, heat conduction. So if we just change our C to a T, so now this becomes temperature, change in temperature with time, is equal to this kappa times the second derivative of temperature with respect to, in this case, depth, which we usually use the letter Z to indicate in most geoscience applications. So this kappa in this case is the same kind of idea as a diffusion constant. It's the thermal diffusivity, and that's a material property multiplied by the second derivative of temperature with space will give you the change in temperature with time, and you can integrate this then to get an equation for calculating what the temperature would be if you wanted to do that. Now, advection as a sort of mathematical equation doesn't look that different. We have, again, a dt dt term here, so change in temperature with time. In this case, multiplied by a scalar, which is Vz. And that's representing then a velocity. And since we're considering this problem in one dimension, which is only vertical, it would be the vertical component of the velocity that matters here, multiplied by now just the temperature gradient, so dt dz. So the idea here would be basically that we could calculate the change in temperature from advection just as a product of the velocity at which the material is being moved and the gradient in temperature. So it looks in many respects similar to the diffusion equation, but we have a first derivative instead of a second derivative. And that's one of our key differences. So our change in mass or energy with time is proportional to the gradient, which is just the first derivative, rather than the curvature or the change in the gradient. And our coefficient here, the velocity in this case, has units of length over time rather than length squared over time, which is what you would have for kappa in the equivalent for heat conduction. So there's some similarities here, and it makes it relatively easy to combine these two because you can say dt equals this, dt equals that. So you can set the two equal to one another and start solving from there, which is what we'll see in the example solution that I'll show you in a moment. But this, as a process, the ideas of advection and diffusion can be applied to heat transfer, just as was mentioned, but also to other things like how river channel profiles change with time. So I don't know whether you're familiar with these kind of river channel profiles, but essentially if you look at the elevation of a river as you go downstream, of course the water's flowing and it tends to flow downstream. So you start somewhere high and move to lower elevations along the length of the river channel. And depending on the type of river, whether it is something that we would consider like an alluvial channel where there's a bunch of sediment on the base of the river, or a bedrock channel, you have differences in how the river channel profile tends to evolve. So for alluvial channels where there's a bunch of sediment along the base of the river, if the channel profile starts out like this with a sort of relatively gentle upper part followed by a sort of steeper part of the river's channel, and then it gets more gentle again, the tendency with time is to behave like a diffusion process. And so over time what you see is that the river steep section starts to get more and more gradual, and the river tends toward trying to basically eliminate this change in the slope along its length. So in other words, what you'll see is that things start out with a sort of gentle, steep, gentle type of river channel as you move downstream, and it becomes essentially something in between the two, but more consistent gradient along the length of the river. And that's because the sediment is able essentially to be moved around in the water, and it will tend to try and make the river have a constant gradient if possible, because it's more or less behaving like a diffusion type of process. So just out of curiosity, these river channel profiles, have you seen this in any courses previously? Like it's normally kind of like a geomorphology concept, but I know there's not really a geomorphology course. Yeah. Okay. Okay. Yeah. I think physical geographers talk about this stuff a bit more because geomorphology is kind of in between geology and physical geography. But in essence, yeah, this is one way in which sediment-choked rivers will evolve over time in terms of their channel length. In contrast, for bedrock rivers where you don't have much or any sediment protecting the bedrock, the tendency is to behave more like an advective process. So if you take the same river profile we had here, where it's a gentle slope up at a high elevation, gets steep, and then gets gentle again, what happens for a bedrock river is that what you tend to see is just kind of an upstream migration of that steep part of the river channel. So if the water in this case is flowing, I guess from the view that we're looking at, from the left to the right, then what you'd see is that this steep section is going to be migrating upstream through time. And so this is the tendency of bedrock channels, is that the shape of the river channel profile doesn't really change with time. It just moves horizontally, and that's the advection part of this. It is, similar in a sense to if you have some, plume of polluted water moving down a river. If you're not mixing very much with the surrounding water in the river as it moves downstream, it kind of just flows down the river at a constant rate. And if there is no mixing, the concentration of that pollutant would also stay the same through time as it moves downriver. Of course, in reality, water is a turbulent substance, so there's always going to be some mixing, so you get a tendency to mix and diffuse that plume of the polluted water as well as it moves downstream. But yeah, this is the kind of process. You could also think with that plume of polluted water example, if you then just stop the river from flowing, that material will just sit in place, but it will start to interact with the water around it. If you dump this into a lake, it will still diffuse and become less concentrated across, with time. It's just no longer moving downstream. So that's more like the kind of diffusion idea. But in essence, you can basically take the same exact two equations here and characterize whether it's heat transfer or advection of some shape of a bedrock channel upstream. You can use the same process or same equations to characterize this. And yeah, I guess there's a couple things that you could note as differences here. Perhaps most importantly is that in the advection equation, there's no assumed conservation of mass. So in the diffusion equation, as we looked at it, we assumed either conservation of mass or conservation of energy. So for a river channel example, that means that here, any place where you have erosion, you have a proportional amount of deposition downstream. So the tendency is that you're eroding from this sort of steep part up here, and anything that's eroded here gets deposited downstream, and that's how that channel then becomes more gradual over time. In the advection case, what happens when this river channel migrates upstream is we just assume any mass that's been eroded is gone. It's just basically carried downstream. The bedrock that the river is carving its way into is all being flushed out of the, at least this part of the river channel that we can see. That's probably an oversimplification, but that's the kind of idea with the advection case here. So yeah, I don't know that we really need to recap the differences between the two equations too much. I think you see it more or less right here, and that is that you've just got a difference in the sort of order of the derivatives. So second derivative for diffusion, first derivative for advection, and also this assumption with the diffusion equation of conservation of whatever the quantity is that's diffusing, whether it's mass or energy, which would be heat, typically for the cases we're considering, or something else. And that's not conserved in the case of advection. So I think I tried to keep that essentially as short as possible just to introduce the concept of advection. Are there any questions about this? I mean, I don't know whether to read that as you don't have any idea where to begin asking, or it was totally clear and there's nothing to ask. But it might also be the case that if we continue a little bit, some questions come up, and feel free, if I haven't said it already earlier, you're absolutely welcome to interrupt me at any point if I'm talking. I've been teaching this topic for enough time now that if I get interrupted, I can easily jump back in wherever. So please, I'd rather that you ask a question if you have one than hold off. But I do also understand that sometimes it takes a little time for a question to come to mind. So for the moment, then, let's continue into our next thing. Again, the slides, I'll put them on the course page after today's class. I didn't have a chance to do that last night, but I'll do that sometime probably this evening. And they'll go here on the course page in the geological advection page where it says the slides will be posted after class. The next thing in today's material is about solving the advection-diffusion equation. And I think for this week and also for next week, if I'm not mistaken, I have examples of how to solve these equations. Not really because you need to do that in order to do the exercise or anything, but more just to show you some of the steps that are involved. And I've been a bit hesitant to take the step to actually make you guys solve and integrate and do these kind of mathematical things that might be somewhat unfamiliar or less often used. So I don't kind of push the issue, but I did want to provide an example of how you can go from, for instance, things like this diffusion equation where you have, dc dt equals minus d, and then the second derivative of c with respect to z or x or whatever. How to go from that to actually getting something where you can calculate what is the concentration and how does it change with time. The most straightforward example to deal with here is to look at the advection-diffusion equation. So to combine advection and diffusion, because as far as heat transfer processes go, again, these two are kind of like best friends, that if you move things from an area where the temperature is hotter or colder to someplace else where the temperature has changed, then you're going to have diffusion taking place after that, which will be the material adjusting to the temperature of the surroundings. And we've seen this now in terms of the change in temperature with time in terms of diffusion and in terms of advection. And to combine the two, it's easy enough. You just add them together. And because they are both in terms of dt dt, no problem there. For the case that we consider in the notes that are on the course page, we consider steady state, which means that the temperature calculation we're going to do is not one in which we consider changes in temperature with time. So in other words, this dt dt, so change in temperature with time term, can be set equal to 0. And in that case, then what you can do is basically rearrange a little bit and end up with an equation that has the second derivative of temperature being equal to this minus Vz over kappa times the first derivative in temperature with respect to, in this case, depth. And you can rewrite this basically as being the derivative of this dt dz. And you can see there's a dt dz on both sides here. And with a little bit of math, we can make some substitutions and come up with a version of our equation that's a differential equation that looks like this, from which we can start solving. So if you're interested to see that, you can go and look through the math here. It's not necessarily something that I feel like it's worthwhile to go through in detail with me just reading off the web page to you, but I'd say if it's in your interest, you can look through there and see examples of how to solve, for instance, the 1D advection-diffusion equation with the assumption of a constant temperature gradient at the surface. That's the easiest boundary condition to use for doing the solution, to get something where you get some kind of temperature as a function of depth equals some stuff. So you can find that on the course page. There's another example of how to do the same thing. I don't show the math, but just in case you're curious about how to do the equivalent solution where you assume that you know the temperature at some depth and you know the temperature at the surface, you can also calculate that example and the equations given here. And finally, then there's this non-dimensional number. So I don't know if you guys deal with non-dimensional numbers ever, but they can be kind of useful in oftentimes in terms of telling you about the relative influence of one thing over another. And in this case, there's a number called the Peclet number that allows you to estimate how much of an influence heat transfer by advection has compared to heat transfer by conduction, to see like which one of the two is sort of dominating. And oftentimes it means if, for instance, advection has a very little influence, you can ignore that term in your equation, which makes the math a lot simpler if you're only dealing with diffusion. So this Peclet number is defined here on the course page, and it's basically just the velocity times the length scale or thickness of whatever the layer is that's moving divided by the thermal diffusivity. And in essence, the idea here is if it's bigger than 1, then that means advection is the more dominant process, and if it's less than 1, of course, the opposite is true. So this is here just for reference. I don't remember whether the Peclet number comes back in, it might come back in exercise 6 or 7. I sort of have a vague feeling that maybe it does come back, but I'm not 100% sure. But it's here if you're interested, and this is quite a common thing for people who do heat transfer calculations to calculate what the Peclet number is for the problem they're solving. And yeah, it's one of these useful non-dimensional numbers. And of course, if you're unfamiliar with non-dimensional numbers, essentially the idea here is that the units of the top term are going to be, well, this would be something like velocity, so meters per second, for instance, multiplied by a distance in meters, which gives you meters squared per second. And then the diffusivity is given in meters squared per second. So when you divide the two, you end up with something that has no unit. And so it's then just a kind of handy number for doing these kind of calculations. So, but this is on the course page, and you can have a look, and you can see, for instance, some of the take-home messages and assumptions here, like we're assuming steady state, so no change in temperature with time. You'll see in this week's exercise, when you include time, the math gets a lot more complicated quickly, and one-dimensional constants are assumed to be constant, which means that they're not varying in space, so the diffusivity is constant across the thickness of the model, and no heat production. So you can find that stuff on the course page if you're interested.